Today we will start Lecture 8-2 on Characteristic Modes, Asymptotic Stability, Initial and Final Value Theorem. Students should be reading Chapter 7 of the course notes in order to follow the lecture. At the conclusion of this lecture, students should be able to define the system terms characteristic modes, dominant poles, asymptotically stable, initial and final value theorem, steady state error, static gain. They should be able to determine if a system is asymptotically stable. They should be able to find the characteristic modes, dominant poles, and system characteristics of a system with a given transfer function. Finally, they should be able to apply the initial and final value theorems to find the gain and/or steady state error of a system with a given transfer function. The characteristic polynomial can be used to describe or find all the characteristics of a system. Given the transfer function h of s equal n of s over d of s, the denominator d of s is the characteristic polynomial of the system. You should recall that this looks very similar to the characteristic polynomial we found in the time domain. The characteristic modes of the system are found from the poles of the transfer function. They are the time domain functions that correspond to the poles. Thus, as seen in prior lectures, the impulse response is the linear combination of the characteristic modes. For example, if the transfer function of a system is g of s is equal to 1 over s plus a times s squared plus 2bs plus b squared plus c squared times s plus d squared, the characteristic modes are the forms of the step response solution in this case. So for example, it would be e to the minus at, e to the minus bt sine ct, e to the minus bt cosine ct, e to the minus dt, and t e to the minus dt. These are the forms that you found when we did partial fraction expansion. Now let's try an example. Determine the characteristic polynomial, characteristic modes, and impulse response for the system described by the following transfer function. 2 over s cubed plus 3s squared plus 2s. So the first thing we do is we factor the denominator. The denominator factors and we get 2 over s times s squared plus 3s plus 2, which factors into 2 over s times s plus 1 times s plus 2. So the characteristic modes would be 1, e to the minus t, and e to the minus 2t. The characteristic polynomial is the denominator of the transfer function. So if I call the characteristic polynomial delta of s, the characteristic polynomial is s cubed plus 3s squared plus 2s. And finally, the impulse response is h of t is equal to a plus b e to the minus t plus c e to the minus 2t u of t. And we can use partial fraction expansion to find these values, and we get that these values are 1 plus e to the minus 2t minus 2 e to the minus t u of t. Let's try another example. 2s over s minus 1 times s squared plus 2s plus 2. So once again, the characteristic polynomial is the denominator of the transfer function. So it's s minus 1 times s squared plus 2s plus 2. So we can rewrite h of s as h of s is equal to 2s over s minus 1 times s plus 1 squared plus 1 squared. So using partial fraction expansion, this could be written as a over s minus 1 plus b times s plus 1 over s plus 1 squared plus 1 squared plus c over s plus 1 squared plus 1 squared. So from here, we can see that the characteristic modes are e to the t, e to the minus t cosine of t, and e to the minus t sine of t. And finally, the impulse response, h of t, would be equal to 2/5 e to the minus t minus 2/5 e to the minus t cosine of t plus 6/5 e to the minus t sine t, and then you multiply the whole thing by u of t. Stability is extremely important for control system design. A feedback control system cannot be designed to regulate to a set value or track at a set point without stability. Bibo stability means that for every bounded input to a system, the output remains bounded with increasing time. We saw this in prior lectures. Another useful definition of stability is asymptotically stable. A system is asymptotically stable if all of its characteristic modes go to 0 as t goes to infinity, or if h of t is equal to 0 as t goes to infinity. A system is asymptotically marginally stable if all of its characteristic modes are bounded as t goes to infinity, or the magnitude of h of t is less than or equal to some integer m as t goes to infinity. Finally, a system is asymptotically unstable if any of its characteristic modes is unbounded as t approaches infinity. All right, let's look at some examples. Determine whether the following systems are stable, unstable, or marginally stable, and these are all with respect to asymptotically stable. H of t is equal to 1 plus e to the minus t u of t. For this one, the limit as t goes to infinity of h of t is equal to 1. So we would say that it is marginally stable. What about h of t equal e to the minus 2t u of t? The limit as t goes to infinity of h of t is equal to 0. So we would say that that one is stable. What about h of t equals 2 plus sine of t u of t? The limit as t goes to infinity of h of t is actually not equal to any number because of the sinusoid, but we can say it oscillates around 2, so you know the magnitude is never going to be greater than 3 or less than 0. So once again, it is bounded less than m. So we would say that it is marginally stable. What about h of t equals 1 plus t plus e to the minus t u of t? Because of that t term, the limit as t goes to infinity of h of t goes to infinity, so we would say it is unstable. What about h of t equal 1 minus t cubed e to the negative 0.1 t u of t? Now this one is a little interesting because of the t cubed e to the minus u 0.1 t. The general rule that we're going to use for this is that e to the minus 0.1 t will die off faster than t cubed will grow. So the limit as t goes to infinity of h of t is equal to 1. So we say that this one is marginally stable. And finally, h of t equal t e to the minus t cosine of 5t plus e to the minus 2t sine of 3t u of t. The limit as t goes to infinity of h of t is going to equal 0, because once again, e to the minus t will die off faster than t will grow, and this one dies off because of the e to the minus t, so that one is 0, and we say that it is stable. The settling time, TS, of a system is the time it takes for the system to reach 2% of its final value. This is 4 tau when we're talking about a first order system, and we can approximate it as 4 tau when we have higher order systems. The settling time can be found from the characteristic modes. To find the settling time, first the system must be stable. Second, the poles of the system must be distinct. And third, the input to the system is a step. For example, if y of t is equal to e to the minus 2t, then the settling time is equivalent to 4 time constants, Ts equals 4 tau. When there are multiple characteristic modes, the overall settling time of the system is determined by the characteristic mode with the longest settling time. The dominant pole provides the longest settling time. It is more difficult to define the rise time, settling time, and percent overshoot for higher order systems. However, some higher order systems can be modeled as first or second order systems if there is a dominant pole or are dominant poles that are significantly far away from some of the other poles on the real part of the S-plane. A good rule of thumb is that if the other poles should be at least 5 times away from the dominant pole for it to be defined as a dominant pole. In class activity 3, for the following system, determine the characteristic modes, dominant poles, and overall settling time. The first thing we're going to do is we're going to rewrite this as if we were going to find the partial fraction expansion. 1 over s plus 1 squared times s plus 10 can be written as a over s plus 1 plus b over s plus 1 squared plus c over s plus 10. So the characteristic modes are e to the minus t, t e to the minus t, and e to the minus 10t. So based upon these characteristic modes, we know that we have a settling time for this one of, if that's e to the negative t over tau, this one would be 4 seconds. If this one is t e to the minus t, then that settling time would also be 4 seconds. And e to the minus 10t, that has a settling time of 4 over 10 or 2 over 5 seconds. So since 4 seconds is longer than 2 over 5 seconds, the pole that produced that is -1. So we would say that the dominant pole is -1, and the overall settling time for our system is 4 seconds. And this is because the one that takes the longest to die off is the one that's going to dominate the system. All right, let's try another example. G of s is equal to 1 over s plus 10 times s squared plus s plus 1. We can rewrite this as a over s plus 10 plus b times s plus 1/2 over s plus 1/2 squared plus the square root of 3 over 2 squared plus c times the square root of 3 over 2 divided by s plus 1/2 squared plus the square root of 3 over 2 squared. So from this, we see that the modes are e to the negative 10t, e to the negative 1/2 t, cosine the square root of 3 over 2t, e to the negative 1/2 t, sine the square root of 3 over 2t. And the settling time for this top one is 4 over 10 or 2 over 5 seconds. The settling time for the second one is 4 times 2 or 8 seconds. And it's the same for the third one, 4 times 2, which is 8 seconds. So the longest settling time is 8 seconds. So the dominant pole is -1/2 plus or minus j on the square root of 3 over 2. And the overall settling time for the system is 8 seconds. In class activity 5, for the following system, determine the characteristic modes, settling time, and dominant pole. 1 over s squared plus 4s plus 6 times s squared plus s plus 1. This can be written as the sum of 4 fractions. The first one is going to be a times s plus 2 over s plus 2 squared plus the square root of 2 squared plus b times the square root of 2 over s plus 2 squared plus the square root of 2 squared plus c times s plus 1/2 divided by s plus 1/2 squared plus the square root of 3 over 2 squared plus d times the square root of 3 over 2 divided by s plus 1/2 squared plus the square root of 3 over 2 squared. So the characteristic modes, there's 4 of them. The first one is e to the minus 2t cosine square root of 2t. Then we have e to the minus 2t sine square root of 2t. Then we have e to the minus 1/2 t cosine of the square root of 3 over 2t, and e to the minus 1/2 t sine square root of 3 over 2t. The settling time for this first term is 4/2, or 2 seconds. And it's also 2 seconds for the second one. And for the third term, it is 4 times 2, which is 8 seconds. And for the last one, it is 4 times 2, which is 8 seconds. So once again, 8 seconds is the longest settling time. So the dominant pole that produced that was -1/2 plus or minus j on the square root of 3/2, and the overall system settling time is 8 seconds. The initial and final value theorems can be used to find the initial and final values of a system response by using the S-domain equivalent of the expression. For example, the initial value theorem states that the limit as t approaches 0 of f of t is equal to the limit as s approaches infinity of s f of s. The final value theorem states that the limit as t approaches infinity of f of t is equal to the limit as s approaches 0 of s f of s. Note that these theorems are not valid if there is more than a single pole at the origin of the imaginary axis. Remember, when there's more than one pole at the origin of the imaginary axis, that means you have an unstable system, so these would not be valid. The steady state error of a system is the difference between the input and output as t approaches infinity. So the steady state error would be the limit as t approaches infinity of x of t minus y of t, or the limit as s approaches 0 of s times x of s minus y of s, by using the final value theorem. If the input is a step function, then x of t is equal to a u of t. So the steady state error becomes the limit as t approaches infinity of a u of t minus h of t convolved with a u of t, or the limit as s approaches 0 of a times 1 minus h of s, or a times 1 minus h of 0. The static gain k of a system is the steady state gain of the system when the input is a step function and all of the transients have died out. If the input is a step function, x of t equal a u of t, which is equal to xss of t, the steady state value of the output, and gain r, y steady state is equal to the limit as t approaches infinity of y of t, or the limit as s approaches 0 of s y of s, which is also equal to the limit as s approaches 0 of ah of s, which equals ah of 0. So finally, k equal to the y steady state over x steady state would be h of 0. So for the following system, determine the static gain, steady state value, and steady state error for an input x of t equals 2 u of t. So the first thing you note is that this is equal to a u of t. So a is equal to 2. The static gain k is equal to h of 0, which equals 1/3. The steady state error is equal to a times 1 minus h of 0, or 2 times 1 minus 1/3. So the steady state error is equal to 4/3. The steady state value, YSS, is equal to the limit as s approaches 0 of a h of s, so that's going to be a times h of s, or a h of 0. So the steady state value is equal to 2 times 1/3, or 2/3. For the following system, determine the static gain, steady state value, and steady state error. H of s is equal to s plus 2 over s squared plus 0.4s plus 3. So once again, the static gain k is equal to h of 0, which is 2/3. The steady state error is equal to a times 1 minus h of 0. And for this one, a is equal to 3, so that's going to be 3 times 1 minus 2/3. So the steady state error is equal to 1. The steady state value, YSS, is equal to a times h of 0. So that's going to be 3 times 2/3. So the steady state value is equal to 2.